In this lecture, we are going to obtain 32 cross 1 marks using 8 cross 1 marks. I was getting this question from you guys continuously, and it was not possible to explain this conversion in comment section. So I'm making this video, and we'll first see how we can have 64 cross 1 marks using 8 cross 1 marks and why it is different to obtain 32 cross 1 marks using 8 cross 1 marks. If we have 64 cross 1 marks, we are going to divide 64 by 8, and we have 8. Again we will divide 8 by 8, that will give us 1. So we have 8 and 1 after the division. It shows we require 9 8 cross 1 marks to obtain 64 cross 1 marks, and it is pretty straightforward. In first line we are going to have 8 cross 1 marks, and the output of this 8 cross 1 marks then will go to the input of this last 8 cross 1 marks, and the output of this last 8 cross 1 marks will act as the output of the 64 cross 1 marks. So this is a very simple conversion, but if we try to do the same thing in case of 32 cross 1 marks, let's see what we have. 32 divided by 8 will give us 4. 4 divided by 8 will give us 0.5. We don't have a whole number in the last division. This shows that we need 4 8 cross 1 marks. This is fine. We need 4 8 cross 1 marks, and the output of this 4 8 cross 1 marks will go to the 4 inputs of the last marks. We are going to use one more 8 cross 1 marks, and this 4 input will go to this 8 cross 1 marks, and the remaining 4 inputs will float. This is not what we want. So whenever you don't have a whole number, in that case you have to use enable. I hope you already know what is enable for a circuit. If you don't know, then enable is nothing but an input that will decide whether the circuit has to operate or not. If we have enable here, let's say this is enable E of this mux, and if this enable E is low, this means this multiplexer is not going to operate, and simply the output is equal to 0. And if this enable is 1, then this circuit will operate. Depending upon this input, we have some output. So we have to use enable, and whenever there is use of enable, the best possible way to obtain the solution is to use the truth table. We require 32 cross 1 marks, and hence I have made the truth table for 32 cross 1 marks. I have not represented the intermediate values because it is not required, and we are going to use this truth table to obtain the circuit. This lecture is very important and very interesting. First I will clear the board, and as you can see we have 4 as integer. That's why we are going to use 4 8 cross 1 marks to obtain 32 cross 1 marks. We will also use basic gates and or not. Let's make 4 8 cross 1 marks quickly. This is the first 8 cross 1 marks, and as we have 8 cross 1 marks, we are going to have 3 selector variables, S0, S1, S2. This is 8 cross 1 marks, and we have one output, and we will have 8 inputs. I will copy this, copy, and then paste. We require 4 8 cross 1 marks. Okay. For the first multiplexer, the input would be I0, I1 all the way to I7. For second multiplexer, the input would be I8, I9 all the way to I15. In the same way, we will have I16, I17 all the way to I23, I24, I25, and finally I 31. So these are our 4 8 cross 1 mux with selector variables S0, S1, S2. Now the important part comes, the role of enable. I'm going to have the enable. This is enable, and remember, this enable is not active low. In some books you will find enable with this bubble, and this enable is active low enable. Whenever the input is low, the circuit will be operational, but in our case the enable is not active low, so whenever the input is low, the circuit will not be operational, and when enable is high, the circuit is going to be operational. So don't confuse yourself with the active low signal. The active low signal is always represented with this bubble, and in this case we are not taking the active low signal. So these are the enable for all these 4 multiplexers. Okay, and let's say we want I0 as the output of 32 cross 1 mux. So what we will have, the value for S0, S1 and S2 are 0 0 0. They are 0 0 0 for all the 4 multiplexers, because S0, S1 and S2 are common for all these 4 multiplexers. They are not different. So we have 0 0 0, and for this multiplexer I0 will be reflected as output. For this multiplexer I8 will be reflected, I16 and I24. Now we will use one OR gate. One OR gate we will use, and output of this OR gate will act as the output of 32 cross 1 mux, and definitely this output will act as one of the input. In the same way, all the outputs of the 4 multiplexers will go to the input of this OR gate, and the output Y will be I0 or I8 or I16 or I24. But this is not how the output of the multiplexers look. We will have only one input routed to the output, and we want I0 to be that input. So we need to get rid of this I8, I16 and I24. So what we can do, we can disable this and this multiplexer. We have to disable them. We have to make E 0 for the last 3 multiplexers, and we have to make E 1 for the first multiplexer. So how we are going to do that? And that we can do with the help of this truth table. Let's say this set of inputs I will call x1. They are output in this table, but they are acting as inputs for this multiplexer, so I'm calling them inputs. And this set of inputs I will represent by x2, in the same way x3 and x4. And now the most important part of this lecture starts. When x1 is high, you can see S4 and S3 are low. So S4 is low and S3 is also low. In the same way, when x2 is high, S4 is low, S4 is low, and S3 is high. Okay, and for x3, in the same way, we can find out S4 is high while S3 is low, and for x4 to be high, S4 is high as well as S3 is high. So this is what we can get from truth table, and we can represent this thing in a more organized manner. So let's do it. X1, S4, S3. Okay, 0, 0. S4 is low, S3 is low. For x2, S4 is low, S3 is high. For x3, S4 is high, S3 is low, and finally for x4, S4 is high and as well as S3 is high. So this is the table that we have obtained, and you can clearly see we require 4 AND gates. X1 is equal to S4 complement S3 complement, x2 is equal to S4 complement S3, x3 is equal to S4 S3 complement, and x4 is equal to S4 S3. So this is what we need, and we have to implement this by using the NOT gate and the AND gate. So I will clear this portion so that we can have our AND gate, and I will cut this and paste this somewhere else. We need 4 AND gates, so let's make 4 AND gates. The output of this AND gate will connect to the enable of the first mux. In the same way, we have to connect the output of the AND gates to the enable, and I am connecting the output of the AND gates to the enable because you can clearly see if the output of this AND gate is 0, it means x1 is 0. X1 is what? X1 is the set of inputs from I0 to I7. It means this multiplexer is not going to operate. In the same way, if x4 is low, it means from I24 to I31 we are not going to get anything, and they are nothing but the input for the last multiplexer. So I have connected x4 to the enable of the last mux, x3 to the enable of the second last, x2 to the enable of the second mux, and x1 to the enable of the first mux. And let's implement this logic quickly. Okay, this is S4. I will use a NOT gate. This one is S3. Again I will use one NOT gate. So this line is S4, this line is S4 complement, this line is S3, and this line is S3 complement. For x1 we require S4 complement, S3 complement. So we need S3 complement and S4 complement. For x2, S4 complement is there, and S3, so S3 and S4 complement. For x3 we have S4 and S3 complement, S3 complement, S4, and finally for x4 we have x3 and x4. This is AND gate 1, AND gate 2, AND gate 3, and AND gate 4. Now let's pick one random output that we want. Let's say the output y is equal to I25. So we want I25, and for I25 you can see we have S4 as 1, S3 as 1. So S4 is 1, S3 is 1. It means x1 is going to be 0, x2 is going to be 0, x3 is going to be 0, and x4 is going to be 1, because x4 is S4 and S3. S4 is 1 and S3 is 1. It means x4 is equal to 1. Simple. And we have enable equal to 0 for this first mux, so it is not operational. In the same way, second mux is also not operational, and third mux is also not operational, but the fourth mux is operational because enable is equal to 1. Now we will focus on S2, S1, S0. S2 is 0, S1 is 0, and S0 is 0. It means I25 will be the output for this last mux, I25, and the output for the first three muxes will be 0, and thus the output, the final output y is equal to 0 or 0 or 0 or I25. And as we already know from the laws of Boolean algebra, this will give us I25. This is what we want. So this is how you have to make 32 cross 1 mux using 8 cross 1 mux. This is a little bit complicated, but if you have followed my lectures, then this will be very easy for you to understand. So this is all for this presentation. See you in the next one.